Hi. On this video, I wanted to work with you a subject which is very interesting uh, from at least from my point of view. Um, we will discuss about how to do a control of the population of mosquitoes and specifically the dengue mosquito. And we will use a technique which is called feedback linearization. So is a very interesting subject and is more like a experiment because um, I'm on the beginning of my studies in dynamical systems, and a warning for you before to entry on the studies of dynamical systems. It's very important to know to have a sense in linear systems. So we have a order to study, but this is not prevent you to start to study dynamical systems, but um, I think it is best if you start from linear systems, and you will see that we have a variety of problems, real world problems like algebraically speaking, an example which is more easy to understand is a linear equation, and we can use a classical one from a line. So that is the equation of the line, and for each x we will have a correspondent y on the line. So this is the most simple example, and this equation is linear because for each point x we have a correspondent on y, but what I wanted to start to work with you on this video is about the control of the population of mosquitoes. And let me just write the technique that we will use. Again, is the feedback linearization. But first, let me on list write what we will be covering, which is the control. And for that, I'm using the book Researches Applied in Math Modulation, which is from Aaron Salsen, Paulo Salsen. I don't know if this is the correct way to pronounce these names, and Sandro uh, Semwick. Selwick. Um, and um, it has more authors collabing with this book, and that's it. It's a very nice book with some um, some problems in math modulation, and this one in specific, I thought it was be a good problem to start, not only to start the studies about dynamical systems, because I'm using other literatures to do this study, which is very nice. So let me list right what we will be doing and what we will be covering. Is the analysis of a model for the population of mosquitoes. So let's see, is the analysis of a model of the mosquito population. Or analysis of a mosquito population model. Analysis of a mosquito population model. And we'll use this technique, which is from control theory. Control theory. And also dynamical system theory. So dynamical system and control theory. Okay, I will not do the introduction of the contest. It's about how to control the mosquito population, the dengue mosquito. The dengue mosquito is a vector of the dengue virus, and this mosquito, it pass this virus, and this virus got people sick, and it's very dangerous. It's something that we must to have a control, and we have prevent measures to control the spread of the virus, like we have vaccines, and but also we have to control the vector, which is the mosquito, and for that we have to apply methods like don't accumulate water, which is points with accumulated water. So on these points, the mosquito will put its eggs. So these eggs will they will develop and grows, and it turns into the mosquito. So this is going to have a exponential increasing, so the population of the mosquito will increase exponentially. So we have to control this population. And This study is about this method. We are doing now a analysis of this method, which is a model for control this mosquito population. Um, and that's it. This little introduction, um, because I don't want it to. Um, it's not my goal, my objective to work the problem, but instead work on the solution. Just a study about the solution, this model, because again, I think is very nice for my studies, and that's it. And this problem is not so simple because we have so many variables involved, and I will try to work step by step on the parts of the problem. We have to formulate um, the model, and I'm just following the book. So I will just describe which uh, it already it was done by the authors, and let me write the name of the book that I'm using is research 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 applied research applied in math modulation. From these authors, okay, and again, I don't want to describe all the intro that is on the book, but something which is very important and is, um, as I was commenting, the way that this modulation it was done, it was for mechanical precautions, like don't let water accumulate it, because where is where the mosquito will put eggs, and these eggs will develop. Um, so this type of precaution, so based on this type of mechanical precautions, which is basically before the the mosquito put the eggs, because after this phase, so we will see that the authors they work with phase, so is the winged phase and the aquatic phase. So on the winged phase, and the precaution is to use insecticide, um, So before the winged phase, which is the aquatic phase, we can apply measures, mechanical measures for control this population, preventing that they become adults, and on this phase, when they are adults, which is the winged phase, they can reproduce, and this will so the population of mosquitoes, they will grow exponentially, and that is bad because again they will spread the the dengue, the virus, and so people got sick and eventually they can die. Okay, so based on these arguments, uh, the authors they propose this um, this model. So first, they describe the dynamic of the population without control, and then after they introduce a control variable to this model to have a control. So then they apply this technique of feedback linearization. So which is important right here is, and I will write this, the feedback linearization is a procedure. Now I'm writing what is on the book is a procedure that allows to transform the dynamic of a non-linear system into a linear one. Um, by, I don't know if is this correct term, feeding back. Let me see. Yeah, it's correct. By feeding back the nonlinear system, yeah, just this, by feeding back the nonlinear system. And the authors also introduce a theory with which is which dealt to us how the model that they uh, present is possible to do this control, and is a theory based on dynamical system. And till now I don't know exactly what they are talking about because um, is a advanced topic, but at least on the intro of the problem, I can describe how they works, what is going on. Um, and again, for me, this is a experiment because I'm on the beginning. I'm just starting with my studies in dynamical systems. So again, we have to know about linear systems first, and then we can jump to dynamical systems, uh, which are a type of dynamical system. Okay, I think we can start. So the authors, they work again with the winged phase and the aquatic phase. So we have the winged phase, and let me put this in order. First, we have the aquatic phase and then the winged phase. Um, so let me type right here. Study about a model of mosquito model mosquito mosquito model population. Mosquito population model. Sorry, mosquito population model. Study about a mosquito population model. So first, on the aquatic phase, we got a variable x1 is equal to x1 of t, which is the density of individuals um, on the population on the aquatic phase. And this is pretty much um, the eggs, the larva, and the pupae. I think is this way how to write. Okay, so this variable it represent um, this first stage of the development of the mosquito. So it's the eggs, the larvae, the pupae, and on the second phase, which is the winged phase, we got x2, which is equal x2 of t, and this t means um, how the variable grow with the time. So for each, for example, right here, x1, for each x1, we have the same x1, but with its growth on the time. It's how its development uh, with the time, how it develops with the time. And this variable x2 is for the unmated females. So is the density of individuals of the population of the mosquito of unmated females, and x3, which is equal x3 of t, and this variable is for the density of individuals on the population of mosquito of fertilized females. Okay, and x4, which is equal x4 of t, and this variable is for the density of individuals on the population of mosquito um, males, and is also considering the mortality rate. So the mortality rate associated to each phase of the development of the mosquito, so is respectively male 1, male 2, 3, and 4 for each phase of the development of the mosquito. So this is for x1, x2, x3, and x4. And we also got the oviposition rates. X1 divided by C, which is proportional to the density of the population, and it will depend of the number of breeding sites and the availability of food. Um, and this phi is the intrinsic oviposition rate, and C is the capacity of the environment. Related to the availability, availability of food. And we also get the parameters gamma, which is the rate of um, the mosquitoes on the phase aquatic phase, how they will move from the aquatic phase to the winged phase. So how the mosquito move to from the aquatic phase to the winged phase. And we have a portion of females on this phase. Females. On from this phase, a portion is female and the other portion is of males. And also beta, which is the rate, is the mating rate. Mating rate. But let me see. Is of immature females. Sorry, immature. Immature females. Immature females mating rate. With males. So with these considerations, the authors, they propose the respective model. So a notation that we use in dynamical systems and in nonlinear systems is this dot above the variable, which means the rate of change. So when I will use this dot, it means the rate of change of x with some respective time, because x is varying with the time. It could be other variable, other dimension, but we are using the time. Now imagine that we have a plant pot. So we have this plant pot, sorry, a plant pot, and is empty, and after rains it got fully with other water. So now the mosquito will come. So now we got the mosquito, and it's a female because just the females got the eggs. So the mosquito will come with the eggs, and it will lay the eggs right here. So we will put And this mosquito can deposit up to 100, 200 eggs, or even 400 a day. So eggs and larvae and pups. So we need to know the mechanism uh, of the development of the mosquito, since from the aquatic phase to the winged phase. So first we have this oviposition rate. So the oviposition rate, it will depend on the capacity of the environment. Um, it will depend if the mosquitoes got food. So we got this variable, which is the oviposition rate, which is directly related to the mosquito. So the oviposition rate is related to the mosquito, how much eggs the female it will lay down on this environment. Um, and it will also depend if this female is fertilized. So X3 is the variable because we can have unfertilized females. So we got fertilized females and unfertilized females. Unfertilized. And if this mosquito is not fertilized, uh, will be related to another variable. Okay, so X3 is for the fertilized females. So this variable is directly related to this mosquito, fertilized female. And now let's see what other variables it relates the first fertilization of the mosquito. Um, right here, we got this one is related to the fertilized female. Right here is unmated females, so it's not related to this first equation of the system. fertilized females we already using. Right here is males, and right here this variable is related to the rate, um, mortality mortality rate of the population of the mosquito. So let's see. I'm following the book, but trying to do a illustration, trying to describe uh, my understanding about this problem. Okay, so we got this gamma, which is how the population, how the mosquito move from the aquatic phase to the winged phase. And minus male one. Okay, so gamma is how much of these eggs and larvae and pups will pass to how much of the individuals on this first stage will turn into mosquitoes. So is the how they will move to this first phase, which is the aquatic, um, to the winged phase. And um, these variables, uh, they are kind of um, telling to us the same thing, because this mu1 is the mortality rate of the individuals on this first stage. So right here, mu1, and right here gamma. And this is of this first stage, the aquatic phase. And we can expand this just to see. So it's gamma times x1 minus gamma times mu1. Okay, so again, this is the oviposition rate, and this x3 is the fertilized females, and because of this we are multiplying these two variables, and gamma is again the rate, how they will pass from the aquatic phase to the winged phase. Right here is the mortality rate And right here is the aquatic phase with larvae, eggs, pups. Okay, to do this modulation, um, you have to know again the mechanic on how the mosquito it reproduces itself. So I try to represent this right here. Um, and we have three equations to complete the system. So this is uh, the rate of change of x1 with a respective time is the dynamic 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 of x or the rate, but dynamic is more correct on this context. Rate of change of x. Okay, this was the introduction, the beginning of what I will try to make a series. This is I consider a advanced topic, and we have more three equations to write to complete this system of equations, this nonlinear system. And again, is indispensable. It is very important to understand the mechanics of how the mosquito it reproduces, uh, and this way, it was the way that the authors they were able to come up with this model. Okay, for now is all. Thank you, and sorry if I'm saying something wrong. Sorry for you that already understand about dynamical systems, nonlinear systems, um, and the more important, I wanted to thank to the authors. Hope there's no problem to reproduce this model on video. I like so much of this book, of the problems that they are presented, and I'm using for my studies. And again, this is just a experiment. Um, I'm a beginner on this subject, dynamical systems, nonlinear systems, and that's it. Thank you. Bye bye.